Okay, picture this. What if you could, like, create your own total solar eclipse? Just switch it on whenever you want, but from space. I mean, it sounds like pure sci-fi, right?
Yeah.
Controlling the sun's light. But the European Space Agency, ESA, they've actually gone and done it. So today, we're doing a deep dive into their really groundbreaking Proba 3 mission. It's just an incredible piece of space engineering, honestly, pushing all sorts of boundaries up there.
Yeah, we've been digging into all the latest info for this, the reports, the scientific releases. There's this great paper, Proba 3, unveiling the solar corona through artificial eclipses.
Hmm.
It really details the first images, the capabilities. It gives you a fantastic picture of what this mission's all about.
Exactly. So our mission today basically is to unpack the amazing engineering behind Proba 3, figure out what these artificial eclipses are telling us about the sun's corona, that mysterious outer bit, and, crucially, why any of this matters for us back here on Earth. So let's get into it.
Okay, so the basic idea, Proba 3 isn't just one satellite. It's actually two, flying together, working like one giant instrument. What are they called, and what do they each, do?
Right. So you have the coronagraph satellite and the occulter satellite. The occulter's job, essentially, is to fly in formation and block the sun's bright disk. And that lets the coronagraph satellite get a good look at the fainter corona around it. Creates the artificial eclipse.
Okay, occulter blocks, chronograph sees, and the formation flying, I heard the precision is just insane.
Oh, it's astonishing. They fly just 150 meters apart,
Hmm.
which sounds close, but maintaining that gap, they do it with millimeter level accuracy.
Millimeters, seriously?
Yeah, seriously. Think about like the thickness of your fingernail. That's the kind of precision we're talking about, 150 meters away. That's already mind-bending. But the really wild part, I gather, is how they do it. It's autonomous.
That's the kicker. It is a genuine world first. These two satellites achieve and maintain this formation entirely on their own. No constant steering from ground control.
Wow. So how on earth do they manage that? What kind of tech are we talking about?
It's it's a whole suite of advanced navigation gear. They use star trackers to know their orientation, standard satellite navigation, radio links to talk to each other, plus optical cameras that actually track special LEDs on the other spacecraft. And there's even a laser bouncing off a mirror and these really sensitive shadow sensors right around the main instrument, ASPICS.
Okay, that is seriously complex. A high-tech dance in space, basically.
You could definitely call it that. It's incredibly sophisticated coordination.
So let's walk through the mechanics then. We have these two satellites dancing perfectly. How does that translate into making an eclipse?
Right, so the occulter satellite positions this circular disk perfectly between the sun and the coronagraph satellite. This disk casts a very small, very precise shadow, only about 8 centimeters wide.
8 centimeters, that's it.
Yep, tiny.
Yeah.
And that perfectly formed shadow has to land exactly on the aperture of the ASPICS coronagraph instrument, which is waiting on the coronagraph satellite. And ASPICS, by the way, that instrument was a big European effort led out of the Centre Spatial de Liège in Belgium.
Okay, so this tiny, precise shadow hits the ASPICS instrument. What does that achieve? What does it let you see?
It's all about getting rid of the sun's overwhelming glare. By blocking the main disk so perfectly, ASPICS can capture images of that super faint outer atmosphere of the corona. It dramatically cuts down on something called stray light, basically, unwanted light bouncing around inside the telescope that usually washes out the faint details of the corona. Proba 3 gets much closer to the sun's edge than previous coronagraphs because of this.
Right, makes sense. So you block the ridiculously bright bit to see the interesting faint stuff around it. Now we've got the how. Let's talk about the why. Why is seeing the corona in such detail so important, especially for, us?
Well, there's this huge, long-standing mystery, the million-degree halo. The sun's surface is only about 6,000 degrees Celsius, but the corona above it, it somehow rockets up to over 1,000,000 degrees.
Yeah, that never made intuitive sense. Hotter, further away.
Exactly. It defies simple physics. And Proba 3's ASPICS instrument is designed specifically to tackle this by getting these super clear views really close to the sun's surface, closer than we could reliably see before. It's gathering data that could finally help us understand the mechanism heating the corona. It's fundamental solar physics.
Okay, so solving a major solar mystery. But there's more to the corona than just temperature, right? Doesn't space weather come from there? Things like the solar wind?
Precisely. The corona is ground zero for space weather. It's where the solar wind originates that constant stream of particles flowing out from the sun. And it's also where we see coronal mass ejections, or CMEs. These are massive eruptions of plasma and magnetic fields.
CMEs, right. They cause the auroras, the northern and southern lights, which are beautiful, but they can also cause problems.
Big problems. Stunning auroras, yes. But powerful CMEs hitting Earth can seriously disrupt our technology. We're talking communications, satellites, GPS navigation, even power grids on the ground. You might remember some significant disruptions back in May 2024. That was linked to strong solar activity, including CMEs.
I do remember that. Flights rerouted, warnings about satellite communication. So Proba 3 observing the corona helps us predict that kind of thing by seeing where it starts.
Exactly. It fills this crucial observation gap. Standard coronagraphs usually have to block out a larger area around the sun. Proba 3, with its external occulter, can see much closer in. It's observing that critical region from about zero 0.8 solar radii. So still above the surface, but very close out to about 3 solar radii. That's the zone where these CMEs often start to accelerate.
A zone we could previously only glimpse during natural eclipses, right?
Pretty much, yeah. And natural eclipses are very short and unpredictable in location. Proba 3 gives us a sustained, regular look at this vital region.
Okay, so it's observing this key area. Let's talk about the results. The first images, when did we get to see them? And what did they look like? Must have been a big moment.
Oh, huge moment. The first proper public release of the inner corona images was June 16th, 2025. And they were pretty stunning. There was this one image taken back on May 23rd, 2025, where the inner corona shows up as greenish. And you can see these incredible hair-like structures. Really fine detail brought out by some clever image processing.
Greenish and hair-like structures. Wow. What else? I heard something about different spectral lines. Like looking at the corona in different colors or something?
Sort of, yeah.
Yeah.
ASPICS can observe the corona in specific wavelengths of light, what we call spectral lines. Each line corresponds to a particular element at a specific, very high temperature. So that green line image, for example. That light comes from iron atoms that have lost about half their electrons because it's so incredibly hot, we're talking up to 2 million degrees Celsius. It basically maps the hottest stuff in the corona.
So you can map temperature by looking at these different lines.
Exactly. They even saw, in one image from May 23rd, a hot loop structure arching out from the sun's surface. That's typically associated with the aftermath of a solar flare. There was also a fainter yellow image from March 25th, 2025, and a violet one, also May 23rd. Those were taken using polarized white light. It's a technique to help separate the light actually coming from the hot corona versus light just scattered off interplanetary dust. Helps clean up the view.
Okay, so multiple techniques to get the clearest picture. And how do they build up the full image? Is it just one snapshot?
No, to capture the huge range in brightness, the inner corona is much brighter than the outer parts. Each full image is actually composite. They combine 3 different exposures, like with HDR photography, to get all the detail.
Right, makes sense. Now, comparing these artificial eclipses to the natural ones we see from Earth, what are the big advantages of doing it Proba 3's way, aside from not having to travel to remote places?
Yeah, that's one advantage. But scientifically, the difference is massive. Proba 3 can create one of these artificial eclipses essentially once per orbit, and its orbit is about 19.6 hours long.
So almost daily eclipses.
Pretty much.
Yeah.
But compare that to natural solar eclipses. You get maybe 1, very rarely 2, somewhere on Earth each year.
Okay, huge difference in frequency. What about duration? Natural eclipses are over in minutes.
Exactly the other key point. Totality during a natural eclipse lasts, a few minutes max? 7 minutes is about the record. Yep. Proba 3 can hold its perfect alignment, its artificial eclipse, for up to 6 hours per orbit.
6 hours?
6 hours of continuous observation of that critical inner corona region. It's revolutionary for studying dynamic events, things changing over time. You can't do that in a few minutes.
Wow. Okay, that is a game changer. Now, ASPICS is obviously the headline act here, imaging the corona. But Proba 3 has other instruments too, right? It's not just about the pictures.
Correct. It's a more comprehensive package. There's DRA, which stands for Digital Absolute Radiometer. Its job is to measure the total amount of energy the sun is putting out, the total solar irradiance. Really fundamental measurement. And then there's 3DES, the 3D Energetic Electron Spectrometer. That one looks at energetic electrons caught in Earth's radiation belts, figuring out their energy and where they're coming from. Important for understanding the space radiation environment.
So measuring the sun's output and the radiation environment near Earth alongside those corona images gives a much fuller picture.
Exactly. It connects the dots between what's happening on the sun, in the corona, and the effects felt nearer to Earth.
So bringing this all together, how are these incredibly detailed, long-duration observations actually changing our ability to predict space weather? Is it feeding into the models?
Oh, absolutely. People are calling it a solar simulation revolution because existing coronagraphs, ones with internal occulters, they just can't see as close to the sun's edge as Proba 3 can with its external occulter design. So this huge flow of observations, as ESA puts it, is providing exactly the kind of detailed, continuous data that modelers need to test and improve their computer simulations, like the Coconut software being developed at KU Leuven.
So better data in means better predictions out.
That's the idea. These improved models can then be plugged into wider systems, like ESA's Virtual Space Weather Modeling Center, the VSWMC. The goal is to create a much more accurate, comprehensive picture of solar events and how they're likely to impact us here, giving better warnings for industries, for satellite operators, for everyone, really.
That connection back to protecting our infrastructure is key. Now, a mission this complex, it must have been a huge international effort, right?
Definitely. You don't pull something like this off alone. Proba 3 launched on December 5th, 2024. It went up from India, actually, from the Satish Dhawan Space Center in Sriharikota on an Indian PSLV XL rocket. And the mission itself involved, I think, more than 29 companies spread across 14 different countries. The prime contractor managing it all was Saner in Spain. But you had major contributions from companies like GMV and Airbus Defense and Space, also in Spain, plus Redwire Space and Spacebill in Belgium, and many others. It's a real showcase of European and international collaboration.
A truly global project for a truly unique capability. And what's the latest on the mission? Is it fully up and running now, fully autonomous?
It's still technically in the commissioning phase, so they're still testing and calibrating everything. The formation flying, while designed to be autonomous, has initially been done under, let's say, close supervision from the ground. The next big step is proving the system is robust enough to achieve that full autonomy, where it just flies the formation perfectly orbit after orbit without routine handholding from mission control. That's the ultimate goal. But even getting to this stage, Proba 3 is already an incredible achievement. It's a masterclass in precision engineering. It's giving us breakthrough solar science, and it's becoming a vital tool for understanding and hopefully mitigating the impacts of space weather. It really is pushing the envelope.
Absolutely incredible stuff. And it makes you think, doesn't it? Now that ESA and all these partners have proven you can do this kind of ultra-precise autonomous formation flying and create these artificial observation conditions on demand, what else becomes possible? What other kinds of artificial phenomena could we potentially create or simulate in space in the future to unlock completely new scientific secrets? It really opens up the imagination.